Okay, the last type of problem we're going to talk about is Newton's law of cooling. And what Newton's law of cooling is all about is how substances cool based on the temperature of their surroundings. A lot of times it's liquids, but it could be objects. And so we'll look at both actually and just kind of walk you guys through the formula. The formula's got several parts to it. I'm just going to go through this quick. So again, this stuff's in your book, by the way, too, so you don't have to necessarily copy it all down, or you can save these notes, of course, if you're doing it on your laptop. But the T of T is the temperature the object reaches after a certain amount of time has passed, so that's going to be like probably our end result, at least for some of the questions. So you bring in a hot cup of coffee, it sits on the table in a room, which is the problem we're going to do in a second. And because the room temperature is cooler, then eventually the liquid cools, and what is that temperature after like a half hour? What's it like after an hour, right? So T of T is temperature the object will reach after some time has passed. T of S is the temperature of the surroundings. So that for most problems, I should say, that'll be room temperature. So, that's, or outdoor temperature, whatever the case is. D sub 0 is the initial temperature difference between the object and its surroundings. That's something you'll have to kind of calculate. It's like a side calculation, let's say. It's probably not a number given to you in the problem, but you can take the temperature of the initial substance and the temperature of the surroundings, subtract the two, and that number will be your D sub 0, or the initial difference in temperature. And then K is a constant that's unique to the object or to the substance. So every object or every substance has its own K. Liquid, any kind of liquid does, solids, your body, everything has a K value. That may be given, you may have to find it. It kind of depends on what the information is. And of course, T is time. So everything, all these things happen with respect to time. When you look at something cooling, if it's just sitting in a room or whatever, it's going to cool over time. So there's the breakdown of the equation. We're going to run through just two examples of this. Pretty good application. You'll see that in a minute. And that'll kind of be it. Then we'll get into the quiz review, and you guys can take your partner quiz. So a cup of coffee has a temperature of 210 degrees Fahrenheit. It's placed in a room that has a temperature of 85 degrees. After 20 minutes, the temperature of the coffee has reached 140 degrees. So a really hot cup of coffee, but the room temperature, quite a bit of a difference. And while it sits in there, of course, it's going to cool, right? First thing is, what's the D sub 0? So we're going to go ahead and just calculate that. Remember, that's the initial difference in the object and the room temperature. So 210 minus 85, or 125. So you're going to need that number as part of your equation. Then it says find the K. So you notice that in this information, we don't have any K. It didn't tell us what the constant is for coffee, the cooling constant. So we're going to have to go figure that out. And because K is up in the exponent, that's going to require you to do that kind of typical solving where I'll get the E part of the equation by itself, and then I'll ln both sides. Same thing we've been doing for lots of problems. So start plugging in some of your information. Now the idea is we do have this temperature time connection. 20 minutes takes us down to 140. So that's going to be your T of T after a certain amount of time has passed. So 20 minutes go by, temperature has dropped to 140. The T of S, remember, is your surroundings. That's going to be the room temperature. That's going to be written in by hand. Right. So you're 85, and then D sub 0, 125. So there's me just plugging stuff into the equation. Okay. Well, what I need to do now again is go ahead and figure out what that K is. And what I'm going to do, like in all problems, I'm not going to take it down to a decimal. I'm going to work through the numbers until I get something that's kind of as best as I can with a fraction, and that's going to go into the actual model. So we're going to get K, and we're going to write a model. Well, as you're walking through the steps, you think about what you got to do. A little bit of algebra cleanup going on, so I'm going to subtract the 85 over, so we'll start with that. So 140 minus 85. And then I get to 125 e to the negative. I'm just going to write 20k just for the purpose of solving, so I'm just kind of shuffling that a little bit. Then go ahead and divide. Now when I divide this, you can leave it as 55 over 125. You could divide by 5, which I think I'll do as far as reducing the fraction. So 55 over 125 reduces down to 11 over 25. And then I'm at e to the negative 20k. Now, if you guys think about this part of the problem, which we've had come up a lot in the last couple of days, I've been asking you guys, hey, can you just look at it and say now the k is without me showing you any more work? And so if you think about what you got to do, it's the ln of 11/25 divided by negative 20. And we've been doing that step, or I've been asking you to try to do that step in your head for like several problems, several days. So by now I think you guys should be able to do that. And that's what you want to use. So when you're going to the model Don't change that to a decimal because, again, you're going to make your problem, your answers inaccurate, so just use that into the model. Okay, so let's go ahead and put our k in now. Yeah, it isn't the greatest looking thing, you know, but we're going to go ahead and just shove that right in there as part of my exponent. So what I put in there was the ln of 11/25 over negative 20, and just put it as my exponent. Now I've got the model, and I'm ready to go. Remember that when you're doing the model, the only variable that should be left should be time. Well, okay, so I got the model. Of course, it's create the model, use the model. That's the goal, again, as you go through these problems. So got the model set up, and now I'm saying, okay, let's find the temperature after a certain amount of time has passed, so 25 minutes. So now I'm going to do the T at 25 and see what I come up with. Now this is just, at this point, it's just you crunching numbers on your calculator. The fact that you have negative and negative, you could at this point, if you wanted to, change that over. Right? Just call it positive. If you like the negative, negative, keep it going. That's okay too. I think I'm going to change it over, just less stuff to sort of keep track of. And then time, which again is the 25. Okay, so if you look at this thing, this is definitely a calculation to practice on your calculator. So I would take a second, try to run through all that, make sure I can do it. Your calculator should actually handle all that in one shot. Like I say that a lot to you guys, but it should if you put it in correctly. And so maybe somebody's there by now. I'm going to go ahead and jot it down. As far as the temperatures go, if you're, I think 1 decimal place is plenty accurate for temperatures. So we're going to go 129.8 degrees. Okay. So from 20 minutes to 25 minutes, you're not noticing a huge change in temperature. It dropped about 10 degrees, right? How long does it take the coffee to reach 90 degrees? So at this point, you're talking about getting pretty close to room temperature. And this also assumes that it's just sitting there, right? You're not stirring it, you're not blowing on it, that kind of stuff. Just sitting there and doing whatever. This will be that kind of problem where I'll have to solve for the exponent t. Now that means your t is going to get kind of messy, the t expression, because look at what the equation looks like already, and now start doing other stuff to it. So I'm going to go ahead and get that set up. Again, I'm working off of my model, which I'm going to grab and pull down here. Hold on one sec while I kind of mess around with some stuff here. I'm going to put it back. Oops. No, that's fine. We'll leave that alone. Let's keep it going, all right? So anyway, what I'm doing here is now 90, right? And also I said I got rid of that negative thing, so we're going to kind of just take that out so I don't have to deal with that. And t is time, that's my variable. So the idea again of this problem is that get it cleaned up, and then of course you're going to have to solve for t by ln log both sides. So by doing a little bit of subtraction, I'm going to have subtract 85, divide by 125, so that'd be 5 over 125. I think if you don't want to use that, it's certainly okay to go down to like 125th. Equals, then I got e2, again, kind of this messy exponent. And t. Now, again, I would ask you guys, can you come up with a t expression without having to do anything else? And really, here's how it would look. You do the ln of both sides, exponent would come down and divide by whatever is multiplied by t. So you'd have the ln of 125th divided by the ln of 11/25 over 20. And there you go. If you wanted to invert and multiply the bottom part, if that made you feel a little bit better, like it was going to be a little bit neater to work with, but I think this is probably just find your calculator and go from there. Anyway, 78.4 minutes, or about an hour and 20 minutes. Okay. Now again, remember that's just sitting there, and also the room temperature isn't actually that cool. An 85-degree room is not exactly what I would call a cool room, so it's not cooling that fast. Right? Okay. I'm going to run you guys through the other kind of problem here, and then we'll wrap it up with this, and we'll move on to review for the quiz. So that's Newton's law of cooling. Now, cooling liquids is an okay way to get you guys started. You get to see all the calculations and do all this stuff. But I think my favorite problem is something like this one that's a little bit more applied. So crime scene investigation. And the body has its own K. Your body has a standard temperature, 98.6 degrees. And this problem is about actually the death. Death has occurred in a crime scene investigation. The investigator arrives on the scene and starts gathering information. And what the investigator wants to know is, first of all, temperatures. Because if I have no other information, no witnesses maybe, or I don't even know who the witnesses were, I need to start getting some information about times things happen. And once I know times things happen, then I can start figuring out, okay, who was there at that time? Look at what else might have been going on during that same time. Businesses were open, people were walking around, whatever. Who saw something or witnessed that kind of stuff. So I need to backtrack using time, and that's what the investigators are going to do. And they're going to use temperature to do that kind of calculation. So it says here, death has occurred, and when the investigator arrives at the scene, the temperature of the surroundings was measured at 65 degrees. Find a model, T of T, so create your model that models the temperature after T hours after the death. Okay, so let's start organizing our information. Now, first of all, temperature surroundings. So I don't know if this is inside or outside, but it's 65 degrees. The D sub 0, remember, is the difference between your surroundings and your initial temperature. Now in this case, while you're still living, your body temperature, 98.6 degrees. So 98.6 minus 65. So you're going to want to get that number. That's like a little side calculation, so make sure that you always do that. So we got 33.6. And so I need those numbers to get started with the model. Now we do know K. K is unique to the human body, so that's, as far as cooling goes, that's the cooling constant for your body, 0.1947. So I have all the information. Actually, it's pretty easy to get it. Just got to put it all in, so I'm going to set up my model. So T of T, temperature surroundings, again, 65 degrees. D sub 0, the difference between my body temperature, my initial temperature, and the surroundings. So 33.6. And then e to the negative, now my k as a decimal, just go ahead and put in 0.1947 and t. So there's the model. Now with the model, and if you're the investigator, you're going to do the same thing. You're going to arrive on the scene, you're going to quick take some temperature measurements, the surrounding temperature measurement, you're going to create your model and get going on the column, get going on your investigation. The next thing I'm going to want to do is check out the time. So in this problem, actually, besides just gathering some temperature information from my surroundings, I'd also want to know what time I arrived, and also what was the temperature of the body. Assuming death had occurred, the body started to cool. And so the idea is, if the investigator got on the scene at 6 a.m. and measured the body temperature to be 75 degrees, at what time did the crime occur? What I'm going to do is, once I gather some information here about the time it occurred, then also I'm thinking about, again, what else happened around that time. Witnesses or whatever I can figure out. Okay, so last little bit of this is to set up our model. Now, 75 degrees actually is the temperature that's the body has reached after a certain amount of time it's passed that I don't know. So what I need to figure out is how much time has passed from the 98.6 to the 75 degree body temperature. So I'm going to take my model and I'm going to plug in 75 as the temperature after a certain period of time has passed. Use my model. And I'm going to solve for t the same way I solve for this in a lot of the other problems. So get it cleaned up, and then once you have the t, we'll say what are you going to do with that. So again, kind of clean it up a little bit. I'm going to subtract 65, divide by 33.6, so that's going to be 10 over 33.6. That's e to the negative 0.1947t. Ln both sides, bring your exponent down and divide, so my t expression is the ln of 10 divided by 33.6 divided by negative 0.1947. And again, I think by now you guys should be able to go from here to here without a whole lot of trouble. Now at this point, what I need to do is I need to get that t down to probably just a single decimal place. So this is one place where I would ask you guys, normally I'd say round a little bit further out, but because we're talking about hours and minutes, you don't want to get too far out. It's going to be kind of hard to get a decent calculation. And as far as time goes, if we're in the area by hours and minutes, we're going to be fine. So 6.2 would be 6 and 2/10 of an hour, or that's 6 hours and 12 minutes. If I'm saying from 6 a.m. and I'm backing my way up, what time is it? 11:48 p.m.